Hello, this is Pete Cachopi. I'm Chief Scientist at Optolytics, and I'd like to give you a brief presentation today about building Pythonic solvers with TICDAT. So what we have here is a checklist that I've put together, try to give some guidelines as to how you can make a mixed integer programming solver or really any prescriptive analytic solver Pythonic. So before I walk through this checklist, let me just get something out of the way up front. I'm not trying to speak against quick and dirty programming or exploratory programming or rapid prototyping or any ideas like that. So Python, one of the great strengths of Python is that it's a scripting language, and so you can whip up a small program very quickly. Or, what I like to do more often is I often just work with inside a Python interpreter I work within IPython, which is a supercharged Python interpreter. And I'm not trying to say that every time you touch Python, you better bang out everything on this checklist. My point is more that once you have established that you have a business problem that's well solved with mixed integer programming or constraint programming or something similar, uh, I think you're well served to go through a checklist like this to make sure that you're creating a really mature product that can be shared with other people, that can be plugged in a modular fashion to a larger system, or even just to make sure that you can put all your work aside, come back to it in 3 months, and get back up to speed quickly. So without further ado, let's walk through these bullet points. So the most important, so I've organized this list essentially from sort of most clearly Pythonic, more clearly adhering to the standards of the Python community, to issues that I think are perhaps more idiosyncratic to these types of solvers, but I think, are well, the issues at the bottom of the list are more my personal strong preference for a wise programming practice in this space. And the issues at the top of the list are more clearly Pythonic. So again, so item one, organize the solver into a package. So package is the terminology that they use in Python for establishing a library. And generally what's going to happen with these solvers is as they get fairly complicated, you want to make it clear sort of what are the public methods and what are the private methods to your engine. And the easiest way to do something like that is with a package. Point two, incorporate testing. So I recommend the unit test library, but there's other ways to incorporate testing. But this is a big point with Python that I think often gets overlooked with more how mixed integer programming is traditionally taught. The way things work in Python, and really more and more with software engineering in general, is that you really are supposed to incorporate testing. So when you build a piece of software, you also build a series of tests that exercise that software. And in the case of mixed integer programming or prescriptive analytics, the nice thing that you get here is that incorporating this testing gives you an opportunity to create a test suite. That's, I think, the most obvious use of the unit test framework. So ignoring the semantics of whether or not creating a test suite should be thought of as unit testing per se, I think having an automated test suite is a really good idea for a solver of any sort of complexity if you're making it as a mature product. And Python does a good job for you in that it's given you the unit test library or other libraries that really can facilitate that sort of automated testing that would go along with the test suite. Point three, organize the package into a repository. So this is just more of a standard, this is more semantics or file organization. So the package, it will itself be a directory, and generally the package lives inside of a root directory that's one level up from the package. And I'll show you that in a second. So that's not too complicated, it's just sort of a standard thing. Publish a well-documented solve function. So here we're getting into the specifics of mixed integer programming. I think the core task that an engine does is to perform a solve. You give it a set of input data and it produces a set of output data, or discovers that the input data isn't feasible and ideally gives you some sort of sensible message. So this is the core task of the solve engine. So you should publish that. You should make that using the package. You should make the solve function publicly visible, and you should document it well in terms of what sort of data it's expecting and what sort of data it will produce. At least sort of the general outlines of the input and the output data should be established, or should be well documented. So to that end, what I'm advocating here is that you should use the TICDAT library to define those input and output schemas. So instead of having to write a long list of true comments, the solve function can essentially be self-commenting. So what I'm saying is, instead of publishing just a solve function, you should have at minimal 3 public members. You should have one public attribute that defines what the input schema is like, one public attribute that defines what the output schema is like, and then a solve function that takes an instance of the input schema and assuming feasibility, produces an instance of the output schema. So essentially, that would allow you to self-document the solve function. The solve function would, in large part, be documented programmatically. Ensure that the solve function validates its input before solving. So technically, I don't think I can call this Pythonic per se, but I think this is sound software engineering practice in general, is to validate your inputs. And the TICDAT library makes validating the inputs relatively simple. So dirty data is simply a part of life. You should take care with respect to dirty data. You should try to identify dirty data before solving. And TICDAT makes the identification of dirty data fairly easy. So without further ado, let's jump into a code example. So here we have a repository for the diet model. So the classic diet model that everyone loves. What I did is follow that checklist that I just gave you, and created a Pythonic engine based around the diet model. So this is the root. So the root directory for the repository is example-diet. There's an explore section. This is where I like to keep notebooks. This is a standard practice that I like to follow, is along with most of my solvers end up being complicated enough that I want to make notes about certain things or about unusual cases, and I create notebooks that document those notes or use cases, and I put them in the explore section. So we'll look at that in a second. For now, let's dive into diet. This is where the package is implemented. So in this case, of course, diet's very simple, so I only have 2 files, and one of them is just the boilerplate of identifying which package members are public. So, but of course, solvers get complicated, and the typical solver that I implement has, several files and subdirectories and all kinds of stuff like that, right? So, but I'm just giving you the most simple one so that you can focus on what's new. So if I look inside this init file, this is a standard Python thing. If you make this file __, if you make the init.py file, then simply the presence of the init.py file establishes that the directory which contains it is a package. And then within the init.py file, you can follow this code like this to indicate what the public members of the package are. So anyone using the diet package they may be able to work around it, and if they want to, they might be able to sort of hack around it and find other members, other functions. But the ones that will be obvious and easy as the public members of the diet package will just be these 3 attributes: the data factory, the solution factory, and the solve function. So the 3 attributes that I talked about before. So now let's look at dietModel.py. So the code here is copied from the Gurobi diet example, and if we skip down to the solve function, I think if you have some familiarity with the Gurobi example for diet, it should be pretty clear that my solve function here, this, what is it, 45 lines of code, are very similar to that, to the code that's on the Gurobi webpage involving diet. So I'm going to draw your attention first to some TICDAT specific things. So first of all, of course, here I am importing TICDAT, and from TICDAT, I'm going to import the TICDAT factory and freeze me. I guess I haven't discussed TICTAT's discussed in a previous video, but I haven't discussed it briefly in this video yet. TICTAT is an open source library created by Oppolytics in order to facilitate more Pythonic solver development and also to facilitate building solvers that can be deployed on our system. So we at Oppolytics see it as sort of a two birds in one stone, right? If you use TICTAT, even you feel you are free to use TICTAT however you want to use it, and we think even without having a business relationship with us, you might find TICTAT useful for building better solvers. But if you also use TICTAT, you will naturally build solvers that are more easily deployed on our system. So again, here I'm making the case about how TICTAT can make your solvers more modular and more Pythonic. So again, let's go back to the three sections, right? The data schema. The three sections of the diet package are the input data schema, the output data schema, and the solve function. So here I am defining the input data schema. That's this block of code. This block of code does the basic definitions of, it lists the table names and the field names. So in this case, for the diet example, there are three input tables: categories, foods, and nutrition quantities. And for each table name, I'm listing the field names, and I'm grouping the field names into primary key fields and data fields. So for example, for the categories table, there's one primary key field called name and two data fields, min nutrition and max nutrition. For the foods table, there's one primary key field called name and one data field called cost. And for the nutrition quantities table, there's one primary key field called food, another primary key field called category, and a data field called quantity, or QTY. So bear in mind that just because I'm defining things in terms of tables and fields, you're not restricted to reading and writing the data only from databases. In fact, TICTAT, with this same code, you can use TICTAT's readers and writers to read from Excel files or CSV files or Access databases or SQLite databases. So I think that's one of the great strengths of TICTAT, is that you can focus on writing the math engine and not worry about the file I/O. As long as you define your requirements of your input schema as long as you define the input schema and the output schema, then TICTAT knows how to do the file I/O for you. I think you'll find it a lot easier to use TICTAT than to try to use the XLS or the CSV libraries directly. Like those are not. I think you'll find this much simpler, in addition to making your code much more robust. So the solution factory is very similar. This is where I'm defining the tables and the fields for the solution. You can point out that really this is the only table that you need. You need to know for each food what's the quantity of food to purchase. But it's always useful to have some ancillary, or it's almost always useful to have some ancillary information returned with the solution. So I'm also creating a table that can keep track of how much nutrition is consumed for each category of nutrition, and just a parameters table where you can just store a single record with the total cost. The parameters table here is an example of a table that doesn't have any primary key fields. So both of those extremes are possible. You can define a table that has nothing but data fields and no primary key fields, or the reverse, a table that has only primary key fields and no data fields. So this section of the input schema is technically optional, but it's strongly encouraged. This is the section where I'm defining the data rules. So here I'm defining how the subtable of nutrition quantities matches with its two parents tables. So when nutrition quantity matches with the foods table, the food field needs to match on the name field. And when the nutrition quantities table matches with the categories table, the category field needs to match with the name field. So hopefully this is fairly common sense to you. It's possible that, OR people don't necessarily study database theory, so the name foreign key, it might be new to you, but I think it's an intuitive concept that you're probably already familiar with, right? I mean, these nutrition quantities records don't make any sense unless this food is a real food and unless this category is a real category. So that's all that's being established here. And then with this section, it's even more straightforward. I'm defining the rules for each of the data fields. So the data fields are min, max nutrition, cost, and quantity. So the easiest thing to do is just to call set data type on each table name, field name, and that gives you the default data type, which is a non-negative, non-infinite number with no integrality restrictions. And in this case, I need to override that behavior for the max nutrition field because I need to allow infinity to be a valid value. So the way we describe that is we say max that the infinity value is an inclusive max, and as opposed to the default, which is an exclusive max. So now that we have rules for all the data fields and rules for all the child-parent relationships, the first thing the solve can do is validate that the data input is correct. So the first thing we do is we want to make sure we're past a dat object. We want to make sure that dat object is itself a tick dat object with the correct tables and field names. That's what this line does. Then we want to make sure that the subtables match with the parent tables correctly. So that's what this line does. Then we want to make sure that each of the data fields has a valid entry in it. And that's what this line does. So essentially we've created, so this is what I mean by self-documenting, self-validating. This is the document up here. We programmatically document what the input data is supposed to look like. We programmatically document what the output data will look like. And then we validate that the input data makes good sense before we jump into a lot of elaborate mathematical processing. So I'm going to go through this section fairly quickly. The main thing I want to highlight is what's special about TICDAT. So I guess the first thing I want to talk about before I even get into the TICDAT business a little bit is just to, for people coming from a background in OPAL or AMPL, those languages which are dedicated to this idea of building mixed integer programs or performing advanced prescriptive analytic modeling, because those languages are so focused, they're going to render algebraic equations more naturally than you can with Python. So in Python, code like that I've highlighted here is about as close as you can get to just writing out mathematics and having it be valid code. Now that said, I think if you just give it a try, have a little experience with this, you'll get to the place that I'm at, which is I can look at something like this and very easily read it as algebra just as easily as I could read sort of a normal, mathematical paper. So, I mean, I think you would agree that at some level this is a lot better than if you had a primitive API where you had to explicitly set the coefficients. I mean, I've written code like that before in C, and it's much, much harder. So, whereas this is perhaps not quite as pretty as the dedicated modeling languages, this is still quite good. And I think it's reasonable to live with this, to live with this slight inconvenience in the legibility of the mathematics in exchange for all the many other advantages you get with Python. So, in other words, what I'm saying is Gurobi did a good job, with their API and brought you as close to true mathematics as you can get in Python. So let's look at this area of the code really briefly. So what's happening here? So again, this is the object that has the input data. You can think of this as being roughly equivalent to an access database, although you can read it from any data source. So it's conceptually the equivalent of an access database. This would be the equivalent of the categories table in that database. And this code here means that I'm referring to that table as if it was a dictionary. So by default, what TICDAT does is it renders tables as dictionaries of dictionaries. We encourage you strongly to sort of standardize how you want to represent tables in your Python code. I think there's two sort of obvious choices: the sort of more Pythonic, the more simple, the more basic Python way to represent a table, and the more what they call it is Pythonic or Pandonic. So you can use pandas data frames to represent tables, and that's sort of beyond the scope of this talk. But TICDAT does support data frames. So if you want to use pandas data frames, throughout your code, I'd like to have a discussion about that because I've worked up some complicated examples and I've worked through a lot of the issues there, and I think that would be an interesting sort of series of conversations to have is how to write Pandonic mixed integer programming code. And but that's a separate. You can look at those examples. I have them up on TICDAT. For now, let's talk about the more straightforward way to represent tables in Python, and that's of dictionaries of dictionaries. So that's what this items function is doing. It's doing what items does for any dictionary, which is give you a list of the keys and the values. So the keys match up to the primary keys. So if there's only one primary key field, the key will be a single element. And if there's more than one primary key field, then the keys will themselves be iterables. And regardless, the values of the dictionary are always themselves dictionaries, and those inner dictionaries are indexed by the data field names. So in other words, each one of these n values is a dictionary with key min nutrition and max nutrition, because min and max nutrition are the fields up here. So I think this way of rendering the data, it might sound a little tricky at first because you have dictionaries of dictionaries. But if you load these things up in IPython and just play around them with a little bit, you'll get the hang of it pretty quickly. And I think, like I said, I think this is really the most natural way to represent tables for mixed integer programming. It's also very close to what you see Gurobi doing in their example set. For a lot of their examples, they go to something that's very much like dictionaries of dictionaries. So that's the default for TICDAT, but there is a way to do pandas if you want. So this code here is again doing something very similar. So again, bear in mind that in this case, the inner dictionary is always a dictionary. So even though the foods table has only one data field, okay, it only has one data field cost, TICDAT will still give you a dictionary even though that dictionary only has one entry in it. So you always, when reading the data from the table, you always have to specify, when you want to get an actual number or an actual value out of the table, you will always end up at some level specifying the name of the field. So for example, down here, again, nutrition quantities is again similar in that there's only one data field. But if you want to look up the nutrition quantity for food for category C, as in food F, then here is the equivalent of an Access database. Here is the table of the database. Here's the nutrition quantities table of that database. Here is the row in that database that matches food value F, category value C. And then here is the value of the quantity field at that row. So this is the kind of code that I write a lot because I like using TICDAT in my own solvers, and I find it very legible and very natural to write it this way. Now, when it comes to writing out the values, so there's two main things you'll need to be doing when you use TICDAT inside of your solve functions. You'll need to be reading from tables and writing to tables. So when it comes to writing to tables, here you have some examples. Example code here, right? So I guess the very first thing you do is you make the solution object. So you call the TICDAT member, you call the TICDAT attribute of the solution factory, and this will give you an instance of a TICDAT class as pertained to this schema. So now SLN is like an Access database that has all the right tables and fields, but no data in them. So now you have to add rows to those tables. And the easiest way to do that is you just, similar to using a normal Python dictionary, if the entry isn't in the dictionary, you can just say that the key, you can just index the key for that for the dictionary entry that you want to add as the left-hand side of this assignment statement, right? So I'm going to assign, for key F, I'm going to assign this value. So you might be saying, hey, wait a minute, I thought you said that it's always dictionaries of dictionaries, and now you are assigning a specific value instead of assigning a dictionary. So let me walk you through that really quickly. So what's happening here is yes, the naive way to do assignments to a dictionary of dictionaries is that you always say the left-hand side is assigned to the inner dictionary. And then you make sure the inner dictionary has the right field names. In this case, the field is QTY for both tables, right? So this is the naive way, or not necessarily the naive way, but this would be the most sort of consistent way to write data to a TICDAT table. But I've tried to make your life easier by doing some overrides. So one override that I've given is that you can add a row and set a value and set the value in that row all in one statement like this. So this statement, when it tries to assign to the quantity member of the inner dictionary, if the inner dictionary isn't there, then it will make it and give it the field names, right? So this is a useful behavior that's required some overrides on my part that works for all of the TICDAT tables. If you want to, you can just say the row, you can just look up the row and then refer to the field in the row. And if the row isn't present, the TICDAT will make the row for you and use default values for all the other fields that aren't being set by this assignment statement. So that's one set of overrides that I did for convenience sake. And then the code I'm showing you here is even a little bit more sophisticated. So when I try to set the whole row to just a single value, what TICDAT does is it says, hey, if this is a table that has only one data field, I don't need to have him specify the field name at all. I mean, it's obvious. There's no choice as to what field he's talking about because there's only one data field. So if there's only one data field, you can write code just like this, except omitting this, because it's obvious there's only one choice for what that highlighted section can be. And so that's what I'm showing you here. So you can use any of these three methods for writing the data, whatever one is easiest to you. As much as possible, I like to do it this way because I think it's more readable. So I think I'd just like to show you very, very quickly. So I don't want to go too much into the testing section for purposes of, knowledge overload in just one talk. And also for a couple other reasons. So one other reason is that the testing section, this requires sort of a priori understanding of things like the unit test library, and this audience might not have studied those sorts of things as of yet. So if you want to study this, I mean, I encourage you to become a mature Python programmer and to study how unit tests work. And this is a good sample code to study, and then cross-reference this code with the documentation for the unit test package. So that's one reason I'm leaving it aside for now. The other reason I'm leaving it aside for now is because it would be wonderful if we would arrange some business arrangement whereby you could build your solvers and Operalytics could deploy them. So to that end, one of the services we offer is not just deploying your solver with a GUI, but we could help you write this testing section, since we understand that what people really like to focus on is this sort of the sexy math part. So this testing section involves a lot of Python code, and if you want us to bang that out for you, if you want us to cooperate on that section with you, that is one of the services that we can provide. I would like to point out one thing, that regardless of whether you use our services or not, the TICDAT library is there to help you make this section, and particularly the TICDAT library is there to help you build this file here. So in this case, we're using the unit test to implement a test suite, and the test suite only has one data file, but in the future, one would assume you would flesh it out with many data files. This data file is stored in this single file readable format that we're calling .sql. So this is a series of SQL-lite statements that would assume a SQL-lite database has been created in the correct fashion, and then it only needs its rows populated. So this file essentially is a human readable file that can refer to many different tables, and it has the advantage that it's very easy to create this file. So the sort of data you would naturally encounter, I would assume, would be in CSV format or XLS format, and that's not the most convenient format for storing the data in the repository. So if you want to store the data in the repository, I created this notebook here to give you a quick demonstration of how you can use TICDAT to convert data from the XLS format to the SQL format. And then the SQL format is ready to store inside a repository. Okay, I think that covers all the main bases here. Thanks for your patience. Please feel free to contact with me if you have any questions. And hopefully you enjoyed this video and might enjoy some other videos we have.